Hello everyone, section 4.2 reflections, example 1. We're going to graph triangle ABC with vertices 1, 3, 5, 2, and 2, 1. So this is A, B, and C respectively. And we're going to reflect this triangle in the line x equals -1. So here's the line x equals -1. And how do we do the reflection? Well, this is like the mirror. A prime is going to be the exact same distance away from the line as A is, and the segment that connects A to A prime will be perpendicular to this line, and it's going to be bisected by the line of reflection. So A is 2 units away, A prime is 2 units away. B is 6 units away, B prime is 1, 2, 3, 4, 5, 6 units away. C is 3 units away, 1, 2, 3 units away. There's C prime. And there's the triangle A prime, B prime, C prime. On a quiz or a test, I'm probably going to want the coordinates. So -3, 3, -7, 2, and -4, 1. That's example 1, part A. Example 1, part B. We're going to reflect this same triangle, but in the line y equals 3. So I'm actually not going to use this graph. I'm going to do this one up here. So the line y equals 3 is right here. And A doesn't move. A prime is the exact same point because it's on the line of reflection. The point on the line of reflection stays on the line of reflection. It's like putting your finger on the mirror. If you put your finger on the mirror, your finger's touching your finger on the mirror. So that's what A and A prime are doing. B prime, 1 unit up. And C prime is 2 units above the line of reflection. And I'm going to put double primes on there because I've used the same graph. I don't want them to get confused. It's part A and part B. So part A's answer, part B's answer. Example 2. Segment AB, that didn't print, but it is on your screen, with endpoints A and B, and its image after a reflection in the line y equals x. So my graph didn't print out. So I'm just going to create one here. Okay. Point A is at 3, -1. So there's point A. Point B is at 3, 2. There's point B. And here's segment AB. And I'm going to graph the reflection in the line y equals x. So where is the line y equals x? The line y equals x goes through 1, 1, 2, 2, 3, 3, 0, 0. 1, 1, 2, 2, 3, 3. So there's the line y equals x. And B, or yeah, we'll do B because it's closest, is going to reflect right over to here. So this is at 2, 3. There's B prime. A prime is going to reflect. You could do it algebraically, but we're not going to. The slope of this line is 1, so the slope of B prime must be -1. The slope of A prime must be -1. 1, 2, 4. A prime. So B prime ends up at 2, 3, and A prime ends up at -1, 3. And that's example 2. Example 3. A little bit harder when the graphs didn't print out. So we're going to reflect the exact same segment A, B, and we're going to do its reflection in the line y equals -x this time. Since I don't have my graph printed out here, I'm going to use this one. So the line y equals -x goes through -1, 1, -2, 2, 1, -1, 2, -2, has a slope of -1. There's the line y equals -x. A prime will end up, my eyes are good, here. Call it a double prime because I'm using the same chart at 1, -3. And B, 2, B prime ends up B double prime, -2, -3. So example 2, example 3, example 4. So this is triangle A, B, C with vertices A, B, and C. And we're going to graph a glide reflection. So it's going to this tells us the rule for the glide, or the translation part. X doesn't move, Y moves down 6, and we're going to then reflect after that in the Y axis. So Yeah, it looks like I'm probably going to need that 7. Okay, so point A is at 3, 2. There's A. Point B is at 6, 3. 1, 2, 3, 4, 5, 6. 2, 3. And point C is at 7, 1. There's our triangle. Let's do the glide, which again the rule tells us to go down 6 spaces. So for A, 1, 2, 3, 4, 5, 6 spaces. A prime, B prime, 1, 2, 3, 4, 5, 6. And C prime, 1, 2, 3, 4, 5, 6. And now we're going to do a reflection in the y-axis. So this is my mirror. A is 3 units away. A prime is 3 units away. A double prime, also 3 units away. A double prime. B prime is 6 units away. So B double prime is going to be here. And let's see, 1, 2, 3, 4, 5, 6. There's B double prime. C prime is 7 units away. C double prime. There is triangle A double prime, B double prime, C double prime after the glide reflection. Okay, now example 5. We have an isosceles triangle, and the picture didn't come out, so I'm just going to draw one. There's our isosceles triangle. We're going to draw all the lines of symmetry. There's only one. Now in the answer key it shows 3. That's because when I originally created this problem I had this as an equilateral triangle. I've changed it to an isosceles triangle. So there's only one line of reflection. Isosceles trapezoid. Do that one over here. Again, there's only one line of reflection going down the middle like that. Isosceles trapezoid. And the picture for part C didn't come out. It's right here. It's this star inside of a square. So there's a line of reflection through each of the vertices of this star. So 1, 2, 3, 4, 5. 5 lines of reflection through the star. That's example 5. Example 6. And again, the picture didn't print on mine. But that's all right, because really this comes down to, here's the canal. The canal is going to act like a line of reflection. Here is Waterville. Here is Drayton. Possibly that's reversed, because I don't have the actual picture. And what we want to do is we want to put a pump on the canal, somewhere on the canal, and then connect that pump to Waterville and connect that pump to Drayton. And we will use the least amount of pipe to connect from Waterville to the pump and the pump to Drayton. So how are we going to do that? Well, this really comes down to a straight line problem, meaning the shortest distance between any two points, between W and D, is a straight line. But the canal is not between Waterville and Drayton. It's down here. So how do we still use a straight line to connect Waterville to Drayton when we have to go to the pump as well? Well, that's where we use reflections. Big surprise. This unit is on reflections, and we're going to use reflections to solve this problem. To do this, we're going to use the canal as a line of reflection, and we're going to reflect either W or D. It doesn't matter which one. I'm going to reflect both to show you that it doesn't matter which one it is. So W prime will be right here. You know what? I have this compass. Let's use it. Set my distance. There we go. So that is W prime. D prime. Is right there. Now, we said the shortest distance between 2 points is a straight line. So if I connect W prime to D, shortest distance is that connection. Or if I connect W to D prime, still, shortest distance. That one dotted. So this is where our pumping station needs to go. How do I know that? Well, reflections are isometries. They're isometric transformations. They're rigid motions, meaning that they retain congruency. So W to P is reflected in W prime to P, meaning that segment must be congruent to that segment. Or D to P, segment DP, has to be congruent to segment D prime P. And if D prime D is the shortest distance between D prime and D, then W to P to D has to be the shortest distance, because they're the same length. Another way to illustrate this is if I put another P out here and I try putting in pipe like that, how do I know for certain that this is longer than WPD? Because this is not the shortest distance between W and D prime. In fact, it's a much longer distance. And W to here to D is the same as W to here to D prime. So that's where my pumping station ends up going. Okay, I'm going to use the picture for example 7 because it didn't print out. And I'm going to show you. So this is like a mini golf problem, right? Where we're going to go off two walls to get the ball into the hole. Now, we can't go straight to the hole. There's walls in the way. We just can't. We have no short straight line distance to there. So, again, we use reflections. We reflect the hole down here, H prime. We reflect the ball over here, B prime. When we connect B to H prime, we get the 2 points on the wall that we're going to aim for. So we go from the ball to the first part of the wall. It's going to bounce off the wall. And you'll learn in physics that angle of incidence is equal to angle of reflection. So angle of reflection is equal to angle of reflection. And then it's going to come off. It's going to hit this wall, and it's going to come off the wall at the exact same angle and go in the hole. Of course, this is assuming there's no left to right spin on the ball. There's only forward spin on the ball. Left right spin in pool would be called English. We're not putting any English on the ball, so when it hits the wall, it comes off at the exact same angle, and in the hole it goes. That's example 6. Classify each statement as true or false. A reflection preserves lengths of segments. That is true. It's a rigid motion. An isometric transformation, it preserves the lengths of segments, congruent. A reflection preserves angle measure, also true. Again, because it is a rigid motion, isometric transformation. Pre-image and the image are congruent to each other. Reflection preserves slopes of lines. That is false. We've seen in many of the examples where the slope here is undefined, the slope here is 0. Slope here is undefined, slope here is 0. Not the same slope after we do the transformation. That was example 8. Example 9. Let r sub x and r sub y represent reflections in the x and y axes respectively. In other words, this is a reflection in the x-axis, this is a reflection in the y-axis. We're going to give the coordinates of the indicated point. So we start with point P, and we're going to, we start with -2, 5, and we're going to map it to point P. And I want to know what the coordinates of point P are after we do a reflection in the x-axis. For reflections in the x and y axes that didn't print out on my paper again. So I'm going to go to those rules right here. So if you have a point AB, it's reflected in the x-axis, then we now have a negative b. So in other words, if the point was 3, 4, now it's 3, -4. Conversely, if we're reflecting in the y-axis, then the x-coordinate changes its value from positive to negative or negative to positive. So again, if we have 3, 4, then it becomes -3, 4. And let's now do that. So if we're doing a reflection in the x-axis of -2, 5, then the y-coordinate changes. So point P will be at -2, -5. We're going to do a reflection in the y-axis of the same point, and the x-coordinate changes its value, so it becomes Q has coordinates 2, 5. What was S, the pre-image, after a reflection in the x-axis? So in other words, 4, -3 is the image, and this must have changed from positive to negative. So S had to be 4, 3. Again, working our way backwards from the image to the pre-image, but reflecting in the y-axis this time, the x-coordinate must have gone from positive to negative. So it is 3, negative 1. We're going to do two reflections. We're going to do a reflection in the x-axis of point 4, 2 to P, and then we're going to do another reflection in the x-axis from P to Q. But we're doing a reflection in the x-axis and then another reflection in the x-axis. We end up back where we started at 4, 2. This one's different. We're going to do a reflection in the x-axis. So negative 3, 3, the y-coordinate changes. So P will be negative 3, negative 3. Then we do a reflection in the y-axis. So P, the x-coordinate is going to change. P going to Q, we end up with 3, negative 3. Okay, example 10. Find the image of point O, which is the origin, 0, 0, after two reflections. First in line 1, which is x equals negative 2, and then in line 2, the line y equals x. So how far away is the origin from the line x equals negative 2? Well, it's 2 units away. So its new coordinates, O prime, will be 2 units to the left of x equals negative 2, so negative 4, 0. And then the rule for the line for reflection in the line y equals x is if we have a, b, we switch them to b, a. So again, 3, 4 becomes 4, 3. So negative 4, 0 becomes O prime, O double prime, 0, negative 4. And there's our final answer for example 10. Example 11, again, my diagram did not come out. So here we have the diagram, and A is at 2, 4. A is 2, 4. And I'm going to use our rules for all these changes. All right, a reflection of the image A in the line y equals x. So A prime becomes 4, 2. A reflection in the line y equals negative x. So the line y equals negative x. AB becomes negative b, negative a. So we flip them and we change their signs. So 3, 4 becomes negative 4, negative 3. So now we're going to take A prime and we're doing the reflection to get A double prime. A double prime. So we flip them and negate them. So I now have A double prime is at negative 2, negative 4. So we're going to do now a reflection of A double prime in the line y equals x to A triple prime. A triple prime. Again, we reverse the x and the y coordinates in a reflection in the line y equals x. Now we're going to take A triple prime and make it A quadruple prime in the line y equals negative x. Switch them and negate them. A quadruple prime is 2, 4. How are A and A quadruple prime related? They are the same point. Back where we started. Okay. Example 12. Again, my pictures didn't come out of Da Vinci. That's okay. The work of artist and scientist Leonardo da Vinci has an unusual characteristic. His handwriting is a mirror image of normal writing. When write the mirror image of the sentence Leonardo da Vinci was left-handed, use a mirror to check how well you did. So we're going to reverse the L, reverse the E, reverse the O, is just an O, reverse the N, reverse the A, is the hard one for me to reverse. Reverse the R, reverse D, B, O, doesn't change. D becomes a B. A, again, a hard one for me to do. V stays the same. I stays the same. N gets reversed. C gets reversed. I doesn't change. W doesn't change. Again, A. S gets reversed. L doesn't change. E gets reversed. F gets reversed. T doesn't change. Dash. H gets reversed. A. N gets reversed. D becomes a B. E. D becomes a B. Period. And I think, if I'm lucky, there's a way of flipping this image vertically. Nope, wrong one. There we go. And Leonardo da Vinci was left-handed. Actually came out pretty good. One of the better ones I've ever done. Okay. Why would he do that? Well, if you've been watching me in all these videos, get that back out of there, you notice that I am left-handed, and oftentimes as I'm writing, oftentimes all the time, my hand is covering what I'm writing. It makes it a little harder for you to see. And what happens, my hand goes across the paper and it smudges on the ink and I can't see what I've just written. Well, Da Vinci, if he was writing as a lefty, if he wrote right to left, you see the words start to appear and he's no longer covering what he's writing. So he would write right to left, so it wouldn't cover what he was writing, it wouldn't smudge what he was writing, it wouldn't have to do what I do when I turn my wrist, so that I'm not putting my hand right on top of exactly what I just wrote. And that's why Da Vinci would have done it that way. That's the end of example 12, part B. Thank you very much.